last several days, size of the body of infants in early life seems to have an impact on later outcomes. We've also heard this described as the first 1,000 days, where pre- and postnatal events will establish lifelong physiological patterns that may manifest as disease processes in later life. And we've also heard that it's not just that individual or that infant, but it's also that infant's mother. And now there's starting to be more increasing evidence that it was also the grandmother's nutritional aspects. So this may be multiple 1,000 days process. We've heard about the fetal origins of disease, also called the Barker hypothesis, which is based upon epidemiological studies where diseases in adulthood, such as cardiovascular disease, diabetes, hypertension, obesity, possibly some cancers, can be related to birth weights. So it's because of this relationships of why there's been, I'll say, a renewed interest in the growth of infants in early life. This is an example of what the differences are in terms of the prevalence of glucose intolerance or diabetes as a function of birth weights. And as Dr. Jackson pointed out yesterday, that, well, you can see going from the right to the left, that with decreasing weight, there's a substantial increase in the percentage of impaired glucose or intolerance and adulthood. But the middle range is what we would normally call, I'll put in quotes, normal weight range. And in fact, even within the normal weight range, as you decrease in weight, there seems to be an increasing prevalence of having diabetes or glucose abnormalities. And in fact, if we look at the two ends, which are the minus 2ST, just basically to the 2 plus 2ST range, there's more than a twofold change in the prevalence of having diabetes issues. If we also look at cardiovascular disease, we've heard, and it's been published again in the Barker group, that death rates seem to be related to birth weights. And again, the four middle regions represent, again, in quotes, the normal birth weight range from the 3rd to the 97th percentile. If we look at the infant growth charts, I think if you look at these two infants, you probably don't need much information other than a visual assessment as to what their status is. I think one may argue that neither of these would be representative of normal. But if we come into the normal range and look at them at birth, now the issues are why, or what is it that's difference between these children? We're only talking about 1.4 kilos or about 3 pounds difference in body weight. Here's another example. It shows 3 infants. These are all newborns within a few days after birth. And they're all within, again, the normal weight range. Also, the BMIs would be within the normal weight range. But again, I think you could see that there appears to be substantial differences in their composition, or at least how they look. So what is contributing to the differences in weight? What are the changes that occur with growth? And what is the relevance of the rate of weight gain, sometimes called catch-up growth? These seem to be the areas now of increasing interest. All of these then can be translated into the question is, what is the body composition of infants during early life? We need to know more information than simply weight and height, or the combination of the two. We need to have more information about what is the true composition. Well, if we look at weight, one of the major compartments of the body, of the composition of the body, is water. The second probably major and normal healthy infants is fat. We also have 2 additional compartments of protein and minerals. So this is what we call a 4-compartment model of body composition. To measure this model, one would actually need 4 separate measurements of each of these compartments, would be the preferred way to do this. And it's often called the 4-compartment reference model. And some places have the ability to make these kinds of measurements. But What has happened because of technology and the strong interest in fat, the water compartments, the protein compartment, and the mineral compartments have now been combined to what's called the fat-free mass, or denoted as FFM. I would emphasize this is not a true body composition compartment, but is a sum of 3 compartments. But what this does for us is allows us then to reduce that more complicated but more accurate 4-compartment model to a more basic 2-compartment model, where the weight is simply fat and the non-fat tissues. So if we could measure, or get some measure of the fat-free mass, subtract that from body weight, we now have an estimate of the fat mass. So this is what most body composition methods have used, this basic 2-compartment model, because it reduces the complication of what needs to be measured. Also, you'll see that not just fat, but oftentimes it's the percentage fat that is talked about, and that is simply the estimate fat divided by the weight times 100 to get it to 1%. So how do we obtain an estimate of the fat-free mass? Well, as we said, water is the major compartment of the fat-free mass. And so measurements of body water and using stable isotopes is the preferred, in fact, it's virtually the only method that is used today. There are 2 IAEA publications in the Human Health Series, number 12 and number 13, which don't tell you much, but anyway, the point is that these two publications give detailed procedures and a very clear understanding of how one can go about making body water measurements and what the pitfalls are and what the concerns are, and again, how to do these in a very scientific way. So body water measurements basically can be summarized as, excuse me, as having first an oral dose of water that's labeled with a stable isotope. Typically wait 3 to 5 hours for the tracer to distribute in the body. You want that tracer to distribute within the water spaces. Then you typically will obtain a saliva or urine sample, preferably of 2 mLs, which oftentimes is difficult to achieve, especially in infants. Because these are biological tissues or fluid being collected from the body, they can be stored, frozen, or processed at a later analysis. They don't have to be done at that moment, which has its own advantages. It either has to be assayed with FTIR, which is Fourier transform infrared spectroscopy, or IRMS, which is isotope ratio mass spectroscopy. And which of those methods you would pick will influence back as to which sample you would collect, saliva or the urine. Said another way, that if you're doing FTIR, you can only use the saliva samples. From this then, one can calculate out the pool, the volume in which the dilution of the deuterium tracer has expanded into. You can determine that volume. And then using a couple of interesting constants. By the way, in body composition, we love to use constants, although most likely these things aren't constant. But that gets converted to a measure of total body water. This shows a typical kind of data that one should be obtaining. It shows total body water versus age in the first 24 months of life. Over the first 12 months, the measurements are made at 1 monthly intervals, and then at 6 month intervals after that. These are data for what's called the Butte model, which was published in 2000. There are other models and there are other data. There are a number of ones we can go to the literature and find, but typically they'll look like you see here. Obviously an increase in water is because there's an increase in weight, and also there is a range of possible water values, which is also related to body size, meaning also weight and height. And there are gender differences. I don't show you that here, but we know there are differences between boys and girls. Well, how do we convert that water measurement, again, to get our estimate of fat? We have to use what's called a hydration constant, which is shown here, which is the K, which is the ratio of the total body water to the fat-free mass ratio. Well, you may ask yourself, how can I do the ratio if I'm using water to get fat-free mass? Well, the answer is you have to make a measurement of fat-free mass in a manner that's independent of the water measurement. But if you do that, you'll see that the hydration, at least in early life, is not constant. In an adult, this is typically considered to be a constant, and the value would be at about 0.732. That would be considered a normal hydration for an adult. But there are changes in hydration in early life. Again, this is the results from the Butte model. So if we divide the water measurement by this constant, we get our estimate of the fat-free mass, and from there, we get our estimate of fat. So when you do a water measurement, and in fact, many of these measurements, you are not measuring fat directly, you're measuring the much larger fat-free compartment and taking that difference with weight to get your fat measure. An alternate two-compartment model is based on body density. In this method, we have first the original equation, which is weight, which is fat plus fat-free mass. We also have body volume. And the assumption is that the volume of the body is equal to the sum of the volumes of the fat-free mass and the fat mass. And so simple, I guess chemistry you would call it, says that density of any object is its weight divided by its volume. So the density of the body then would be the weight of the body divided by its volume. Now in this approach, there are, again, assumptions. We have to be able to convert this density information to some estimate of body composition. This is done, again, a two-compartment model. And the first assumption is that the density of the fat compartment is a constant. Typically, the number used is shown there, which is 0.903 grams per ml. That's typically the constant that is used. It's also, if you can see, says that the density of the fat-free mass is almost constant, because we do know it's going to vary with age and gender, because we know that water is the major compartment of the fat-free mass. But if you do these equations at the top, the weight and volume equations and the density equation, one can rearrange these relationships between total body and the subcompartments, both volume and densities, and arrive at an equation which presents the percentage of fat as a constant divided by the density of the body minus another constant. Again, as you can see from the two equations at the bottom of the slide, the K1 and K2s are not true constants, but in fact are related to the density of the fat and the fat-free mass. Now, since we're saying the density of fat is constant, the parameter which we need to have some better measure of is the density of the fat-free mass. There are several papers. There's only actually about 3, maybe 4 papers that have ever reported on the density of the fat-free mass. This one is what's called the Foman model. This is a hypothetical reconstructed model. It's not actual measurements in any infants, but a model that is reconstructed from multiple data sources. And this shows the change in the fat-free mass density as a function of age or the first 24 months of life. There is a difference in the density between boys and girls, and as you can see, they both increase. Now what's interesting is, again, is these increases are very small, in the range of 0.007 to 0.09 grams per ml over 24 months, which is saying that's 0.06% change in a given month. But if one doesn't know the proper age and were to misuse a value from an incorrect age, for example, it would immediately start to